Good evening, sir. My name is Krishank, and this is my presentation for COA case study and simulation. My assigned processor was ARM V8, also known as ARX64. So let's begin. The main agenda of this presentation is it explores the ARM V8 architecture through theoretical studies and practical simulation. We'll examine the architectural foundations that make the ARM V8 processors dominant in this field, and also in mobile and embedded systems. The session bridges theoretical understanding with hands-on experience, reinforcing core computer organization principles including instructions, execution, register, management, and control flow. We also discuss some of the parts of this architecture. It discusses the ARM-based architecture, instruction set architecture, data path, pipeline design, memory hierarchy, specialized features, and simulation demonstration. Next comes the architecture overview of this. There are three main parts of this: the RISC foundation, 64-bit evolution, and power efficiency. ARM V8 follows reduced instruction set computing principles with fixed 32-bit instruction length, enabling simplified decode, logic, and efficient pipelining. The 64-bit evolution introduces the ARM V8 execution state with 64-bit addressing and operations, while maintaining ARM64 compatibility for legacy code. This dual state designs ensure backward compatibility without compromising modern performance. When talking about the power efficiency, designed for optimal performance per watt ratio, making it ideal for mobile devices, embedded systems, and data centers. Powers billions of smartphones and increasingly used in servers and laptops, computers/computers. The main application of this processor is mobile devices, Apple Silicon, server infrastructure, and embedded systems. Moving on. Instruction set architecture, ISA. The ARM V8 ISA provides a comprehensive instruction set organized into distinct formats, each optimized for specific operation type. The architecture features 31 general purpose 64-bit registers plus a 0 register and a stack pointer, supporting both 64-bit and 32-bit register. There are four types of instructions, my bad. R-type, I-type, branch, and load or store. The R-type instructions, register to register, are register to register operations. The format is opcode, RN, shunt, RN, and RD. The I-type instructions are immediate value operations. The branch instructions are control flow operations, and the load instructions are memory access operations. Also, the common addressing modes, the immediate addressing, register addressing, base plus offset. Operand is constant value embedded instructions in immediate addressing. Operands located in registers in register addressing. And memory address calculated from base register plus offset in base plus offset. Data path and pipeline architecture. ARM V8 processors implement sophisticated pipelining techniques to maximize instruction throughput. The basic 5 stages of pipeline allows multiple instructions to be in various execution stages simultaneously, significantly improving performance over sequential execution. The 5 stages are instruction fetch, instruction decode, execute, memory access, and write back. Instruction fetch basically retrieves instruction from memory using program counter and updates PC for next instruction. Instruction decode, instruction format identifies the operation and read register operands. Execute, perform arithmetical logical operations, calculate memory addresses, and evaluate branch conditions. Memory access loads data from or stores data to memory if required by instruction. Write results back to destination register, completing instruction execution. Advanced pipeline features, out of order execution. Instructions can complete in different order than issued, maximizing execution and utilization by avoiding pipeline stalls when dependency exists. Branch prediction. Hardware predicts branch outcomes through fetch and execute instructions, minimizing performance from the control hazards. Superscalar dispatch. Multiple instructions issued per cycle to parallel execution units, achieving instruction level parallelism within a single core. Memory hierarchy. ARM V8 processors implement a sophisticated multi-level cache hierarchy to bridge the speed gap between fast CPU registers and slower main memory. The store architecture ensures all computational operations use register operands with explicit instruction for memory access. Registers are the fastest storage, 31 general purpose 64-bit registers, sub-nanosecond access. L1 cache, L2 cache, L3 cache, and main memory. The main memory management, the MMU in short, provides virtual to physical address translation, enabling memory protection, process isolation, and efficient memory utilization. Base cable maps addresses to physical memory with TLB. Translation look aside buffer. Caching recent translation. And in the store design, ARM follows strict load architecture where arithmetic and logical operations only work with registers and with register operands. Memory must be explicitly loaded into registers before computation and stored back after, simplifying instruction formats and pattern design. Next. Specialized features and parallelism. Beyond the core instruction set, ARM v8 incorporates advanced features for specialized workloads and parallel processing. These extensions enable efficient multimedia processing, cryptographic operations, and virtualization while maintaining the architecture's power efficiency. The Neon SIM engine, single instruction multiple data for now, technology processes multiple data elements simultaneously. Features 32 128-bit vector registers for parallel operations on 8, 16, 32, and 64-bit elements. Accelerates multimedia, signal processing, and machine learning workloads significantly. The cryptographic extensions. Hardware accelerated cryptographic instructions, including AES, encryption, and decryption. And delivers to 10 to 20 times performance improvement over software implementations while maintaining security against timing attacks. Virtualization support for 4 exception levels enables secure virtualization and hypervisor implementation. EL0 for applications, EL1 for OS kernel, EL2 for hypervisor, and EL3 for secure monitor. Multi-core and big little. Heterogeneous multiprocessing combines high-performance core with power-efficient cores. Big little architecture dynamically assigns workload to appropriate core types, maximizing performance per watt. Enables 4 to 8 plus core configurations in mobile and server processors. Then comes the simulation of Fibonacci sequence. We have to generate the first 10 Fibonacci numbers using assembly language code. I use the simulator from MIP S342. While ARM was studied theoretically, MIPS assembly was used for practical simulation due to its support. The concept translates directly register operations, control flow, and memory management principles remain consistent across RISC architectures. The registers utilized are $T0, $T1, $2, $3, and $A0 and $B0. Coming back to the code, this is an assembly code which I have written for the Fibonacci series. Coming to this, first I load the first term 0, second term 1, and then set the counter to 10. Coming to the loop, I print the value of $T0 using syscall 1, then I print space using syscall 4, and then I calculate the next Fibonacci term using add $T0, $T1, and $T3. Then I update the registers from $T0 to 1 and $T1 to 3. Then I decrement the counter and branch back to the loop until I get all the 10 numbers printed. This is how the code runs, and this is the output which I get after all this. You can see all this. This is the output I get after running the code. And thank you for this code and this assignment. It really helped me a lot. That's okay.